Today, hello students. Today we have to see the next topic of our syllabus, energy of particle which is performing simple harmonic motion. So before going into this topic in details, so first of all we know there are two type of energies. One is said to be kinetic energy acquired by the particle or body due to velocity. It has a velocity, so it is said to be kinetic energy. Another energy is said to be potential energy as particle has certain height. Due to that height, it acquired some energy that is said to be potential energy stored in the object in terms of height, we can say. That is potential energy. To find out total energy, we have to add this kinetic energy and potential energy together. It will give the total energy of particle. As particle is performing simple harmonic motion, so it has both type of energy, that is kinetic as well as potential. So we have to find out kinetic energy first, then potential energy. Then when we add both the energies, we get a total energy of particle which is performing simple harmonic motion. And remember, as we know, here also in simple harmonic motion, kinetic energy and potential energy are interconvertible. That means some part get kinetic energy converted into potential energy. At the same time, potential energy is also converted into kinetic energy. So that all of you are well known about this. So this kinetic and potential energy are interconvertible. So suppose we have represent this the total energy of particle performing SHM by E, total energy. Then you can write here one simple equation, E equal to the energy that is said to be kinetic energy plus energy that is said to be potential energy. So it is said to be potential energy. So first of all, to find the total energy, just we have to find kinetic and potential energy and then add them together, we get a total energy. So first of all, we'll find out the kinetic energy. So just look at here on this side, I will derive the equation for kinetic energy of particle performing the simple harmonic motion. So for that, suppose a particle has mass m moving with the velocity v, performing simple harmonic motion, just find out the kinetic energy. We know the formula for kinetic energy of particle as, so kinetic energy of particle can be represented by simple mathematical equation. I will write it at the top a little bit so we get a lot of blackboard to write. So kinetic energy equal to 1 by 2 m into v square. 1 by 2 m into v square is the kinetic energy. And as we know, here particle is performing simple harmonic motion. We have already derived the equation for displacement, velocity and acceleration. If you remember, out of that, the equation for velocity we have written as v equal to plus minus omega square root of a square minus x square. Such type of equation already we have derived. From differential equation of simple harmonic motion, we have find out acceleration, and from that we have find out the velocity. So that equation I have written here. If we put this value of omega in this equation, we get a kinetic energy. Just put it here and we can write this kinetic energy that is said to be E suffix ke equal to 1 by 2 as it is, m as it is. V square means this whole square. It is m omega square in the bracket a square minus x square. Square root goes off because we have taken a square of that term. So it is omega square a square minus x square is the velocity square. Now let's go. Here we know again as we know omega square equal to k by m. This implies that m into omega square is nothing but a k equal to m omega square. So you can put this value of k here. We can rewrite the equation as 1 by 2 k a square minus x square, and that is nothing but a kinetic energy of particle for forming SHM. Suppose equation 1, suppose this is equation 2. Both the equation 1 and 2 are same, only here it is in terms of m and omega square, it is in terms of force constant k, and both the equation gives the kinetic energy of particle performing simple harmonic motion. Now let's see, this particle is performing simple harmonic motion, so we have to draw some diagram here. So let us suppose this is a particle performing simple harmonic motion along this straight line. According to book we will go. So it is nothing but this is the n, this is the m, extreme position, this would be somewhere here mean position O, and particle is performing to and fro type of simple harmonic motion. At some instant, the position of particle will be represented by P, and distance of P from O is suppose x. So this is type of simple harmonic motion is there. Now we have to find out the kinetic energy. We have already find out. We have to find out the potential energy. To find the potential energy, the most important concept we have to consider that as potential energy is nothing but what? It is due to the height, we can say, or we can find out work done. So in terms of work done, that work done required to move the body to certain height is itself is nothing but what? It is a potential energy. So we have to find out work done here. Before going into detail of this potential energy, first of all I would like to tell you one thing. As we have derived a formula as x displacement equal to a sine such type of thing is there, a sine omega t plus phi. One correction we have to do here. Here we have taken this small a square as an amplitude, but according to the book it is capital A square. So let's go to this as a capital A square. Just symbol I have changed. Equation remains same. I have not changed the equation. Symbol they have used as a capital A instead of small a. So that we have done. As we know this is x displacement. Find out the velocity. Velocity equal to dx by dt. So it is a omega. Derivative of sine is what? Cos omega t plus phi. So this is also the equation for velocity. Same thing you can write here as a omega cos of omega t plus phi. It is a velocity. But here it is velocity square. So you can write this as equal to 1 by 2 m. This 1 by 2 m comes. V square we have put this as a square omega square cos square omega t plus phi. So these two equations are again same. This is in terms of trigonometric function and this is in terms of k, this is in terms of m omega square. So I hope you got this as a kinetic energy. Now let's go to the potential energy of particle. Now before going into potential energy of the particle, as we have to consider when particle move from O to P, suppose it is x, and for further displacement, they have used in your book as a word infinitesimally small. Infinitesimally small means what? For further small displacement, suppose this is dx. Particle move from O to P by distance x. For further x plus something, x plus dx, what it will require? It will require work done to go that place. So there is work done, and as this particle is moving to this direction, there must be force, restoring force that act in this direction. This direction of displacement dx, this would be the force F is equal to minus kx, as we have derived this equation. So from this we can find out the work done. Work done required to displace the body from this point P to the small distance dx is suppose that work done is dw. As we know, work done is what? Force into displacement. So it is minus dx. Now the question comes, why we have taken minus dx? Because force and displacements are moving in opposite direction. That's why we have taken as a minus dx. Now put the value of force here from this equation. So you can write this as minus of kx, value of the force, into minus of dx. It becomes what? Plus of kx dx. Work done equal to plus of kx dx. Now remember, this is for small displacement dx. Small displacement dx. Work done is dw we have find out. Suppose I want to find out total work done. Total work done when particle move from O to M. Here at point O, it is mean position, x equal to 0. At this position, x is maximum, x equal to maximum means it is plus a here. Here it is minus a to this side. Here it is plus a. Suppose here x equal to plus a at the maximum side, at the mean position it is 0. So we have to take an integration of this to find out the total work done. So integrate it. So k is constant, take it outside, x dx. Those students who don't have mathematics, don't worry. This is a general formula in mathematics, as integration of dw becomes w, total work done. This becomes w equal to k, and as we have seen that integration of x is what? X square divided by 2. X square divided by 2. So this will give the x k into x square by 2. We can write it as simple 1 by 2 k into x square. Okay, and this work done itself will be stored in the body in the form of potential energy. So we can write this as this work done itself is nothing but a potential energy. So we can write this work done as nothing but a potential energy. So we have derived the equation for potential energy as 1 by 2 kx square. Again, here if you remember, omega square equal to k by m, we have put k equal to m omega square. We can put that value here. So you can write this as 1 by 2 m omega square x square. These both equations are suppose equation 3, and these equations give the potential energy of the particle. These equations give the potential energy of particle performing simple harmonic motion. But as we know, this potential energy we have find out. Suppose I want to find out the same thing by using the trigonometric function. So what we can write here in this equation 1 by 2 k x square. X equal to what? Already we know a sine omega t plus phi here. So if you put that value, you can write it as 1 by 2 k. What is the value of x? A sine of omega t plus phi, and its square it is. So you can write, I will write directly a square sine square omega t plus phi. A square sine square omega t plus phi. So potential energy directly proportional to sine square, while the kinetic energy directly proportional to cos square term. So that is nothing but we have find out both the terms, and as we have written the first equation, and suppose that first equation I will give the name as E. Now we know the value of kinetic energy, we know the value of potential energy. Put both the values in this equation A and rewrite the equation. What we get? The total energy of particle performing SHM that we can find out. So put it, so you can write, put these values in equation A. You can write total energy E equal to, what is the equation for kinetic energy we have derived? It is 1 by 2 k, it is 1 by 2 k A square minus x square. This is the kinetic energy we have derived here. Just look at here. This equation 2. From equation 2, we have put that value. Now here we get a kinetic energy. Now just put this from equation 3. This value, as it is in terms of k, we'll take k. So this 1 by 2 kx square plus 1 by 2 k into x square. So this is equation which is sum of kinetic and potential, which will give the total energy. Now see, 1 by 2 k square minus 1 by 2 kx square plus 1 by 2 kx square. So this x square term get cancelled here, plus minus it is 0. So what is remaining? It remains 1 by 2 k into a square, that is nothing but a total energy of particle performing simple harmonic motion is given by E equal to 1 by 2 k into a square. Same thing can be written as, if you put a value of k as m omega square, 1 by 2 m omega square a square. So this is the again same equation, E total energy equal to m omega square into a square. That is the equation for the total energy of particle performing simple harmonic motion. Is that clear? I hope you got this idea. Now just I hope you know how to find out total energy. Now let's go further. This total energy you can write down in terms of different parameters, different functions. Suppose here it is omega square. If I put this omega, put here omega equal to 2 pi f. There is one formula for this. As we know, T equal to 2 pi by omega. Okay, what is T? T is a time. Time is the reciprocal of frequency. You can write 1 by f equal to 2 pi by omega. So omega goes here, frequency goes here. Omega equal to 2 pi f. By that formula, we can put it here. Omega equal to 2 pi f here. And rewrite the equation. You can write E equal to 1 by 2 m as it is. Omega square means what? 2 pi f square. It is 4 pi square f square A square. So this would be the equation. Again, in this case, if we put the value of force here, not a force, sorry. If you put the value of frequency here, frequency is reciprocal of time, you can rewrite the equation as this 4 2s are 2. So it becomes 2 here. So write down here 2m pi square A square divided by T square. We have put the value here F equal to 1 by T. So we get this equation. And from this equations, these two equations, we can conclude something. That conclusion are nothing but what? The total energy of particle performing linear simple harmonic motion is found to be directly proportional to directly proportional to mass, not the square, it is only mass. Directly proportional to mass, directly proportional to square of frequency, directly proportional to square of amplitude. A is amplitude, it's square, so directly proportional to square of amplitude, or inversely proportional to square of time period. So these are the conclusion that can be drawn. Just in your book there is equation 5.25. Below that they have mentioned the same thing I have told you here. Now there is a one blue color column in your book. Can you tell? It's very simple. Try to find out the answer of this question. See, to give the answer of this question by me, it's not good. It can't increase your logical thinking can be improved. So to improve your logical thinking, it is better to think by your brain on this question. Still, if you don't get it within 2 to 4 days, try to find out. If you don't find it within 2 to 4 days, you can ask me, then I will tell you. Okay, let's go further. There are some special cases they have taken. What are these special cases are? So I hope all of you know this. Just we'll revise this topic within 2 minutes. So first of all, we have written one simple equation. The total energy is sum of kinetic and potential energy. Now first of all, find out kinetic energy, potential energy, add them, we get total energy. Okay, so we know the equation for kinetic energies was 1 by 2 mv square, and we have find out the value of v, velocity for a particle performing SHM is this. Put this value here, rewrite the equation, we get this equation. But here m omega square is k, as we have put this value in differential equation of SHM. So from that you can put it k here. So it is k a square minus x square. If you write down same equation for in terms of what? Trigonometric function, as x equal to a sine omega t plus phi. Take its derivative, you get velocity. Put it in this velocity square 1 by 2 m as it is. Put that value. So this equation 1 and 2 both will give what? The kinetic energy of particle performing SHM. Okay, then we come to this diagram. In this diagram, n and m are nothing but what? Extreme position. O is the mean position. Now suppose particle is somewhere at position P at distance x from origin O. For further displacement of particle from P to very small displacement, infinitesimally small, dx, x plus dx. Suppose the force required is F is equal to minus kx. Displacement and force are moving in opposite direction. Now let's find out the total potential energy. The work done required to move the particle from P to distance dx itself is a potential energy. So that we have find out the work done dw required for a displacement dx. Okay, for the displacement f into minus dx. Minus sign because they are opposite direction. Put the value of s equal to minus kx into minus dx, minus cancelled out, k into x dx. Now this is a work done for small displacement small displacement dx, work done is dw. I want to find the total work done required by particle to move from this mean position 0 origin O to extreme right or extreme left. What is total work done? That can be found out by integration. Find out the integration, we get w equal to kx square by 2, and this w itself is nothing but a potential energy. So potential energy is 1 by 2 kx square. If you put the value of k as a m omega square, then we get 1 by 2 m omega square x. If you put in trigonometric term, so just we can write this. All these are the equations for potential energy. As we know the equation for kinetic and potential energy, put it in this equation E. Then you can write this as the total energy E equal to 1 by 2 a square minus x square plus 1 by 2 kx square. This is potential, this is kinetic. Minus 1 by 2 kx square plus 1 by 2 kx square cancelled out. The total energy is 1 by 2 ka square. Now put the value of k as omega square, m omega square, we get the same equation. So these are the equations for total energy of particle performing SHM. Now if you put here omega equal to 2 pi f, how it comes? Just look at the time period, t equal to 2 pi by omega, but t is nothing but reciprocal of frequency, 1 by f equal to 2 pi by omega. Move this omega here, f here, we get omega equal to 2 pi f. Put it here in this equation. So it is square. So 1 by 2 m as it is, we get 1 by 2 m as it is. 2 square is 4, pi square is pi square, f square is f square, and a square. 2's 4's are 2. So you can add 2m, pi square, a square, f is 1 by t, it's square. So from this you can say the total energy is found to be directly proportional to mass, directly proportional to square of frequency, directly proportional to square of amplitude, or inversely proportional to square of time period. In this fashion, we have just derived the equation for the kinetic energy, potential energy, and finally total energy of particle performing SHM. Now here we have to consider some special cases. What are the special cases means? Let's start. The special cases are nothing but I will just put this equation to, or just I will erase this part. This small part I will erase. I will write whatever the special cases are here. I will write that special cases somewhere here. Okay. So within this part, I will try to write that equations. What are the special cases? I will write within this portion. Okay. Now let's go. What are the special cases? The special cases are nothing but at mean position and at extreme position. That's it. That are the special cases. So as particle is performing SHM, either it remains at mean position or extreme right or extreme left. So the two conditions we have to consider. When particle at this position, it is said to be mean position. What are the value of kinetic energy, potential energy, and total energy at original position, mean position? What are the values of kinetic energy, potential energy, and total energy either at m or n? These are the extreme position. So these two are the special cases only. Let's write down. The first of all, so let us start with the first condition at mean position. Mean position. As it is mean position, what is the value of x? X equal to 0. At mean position, x is 0. Velocity is maximum. Displacement is 0 at mean position. Pendulum comes at mean position. The displacement is 0. Here it is maximum. Here it is maximum. At this position it is 0. X equal to 0. Now what is the kinetic energy formula? Kinetic energy. The kinetic energy equal to 1 by 2. Okay. As we can find it from this equation. 1 by 2 we can write from this equation. Okay, 1 by 2 k a square minus x square. This is the kinetic energy. Similarly, write down the equation for potential energy. Potential energy is this: x equal to 0 here and here. What we can write? As this x is 0, square is 0, potential energy would be 0. This would be 0. Okay, so at mean position, potential energy of particle is always 0. Okay, if you put here 0 this term, what is the kinetic energy? So this kinetic energy equal to 1 by 2 k into a square. This must be capital again. It is symbol. I will use sometimes small a. Basically, according to book, it is capital A. So let's go capital A. So it is 1 by 2 k a square is kinetic energy. So total energy is what? Total energy, kinetic energy, potential energy is 0. So total energy is a kinetic energy, and that is 1 by 2 k into a square. And from this you can say that at a mean position, total energy is a kinetic energy because potential energy is 0 at mean position. That is the first special case. Let's go for second special case. Before going into second special case, let's look at this equation. Let's look at this equation of energy here. E equal to 1 by 2 ka square. Sum of kinetic and potential. 1 by 2 ka square. At mean position, what we get? 1 by 2 ka square. So energy is not changing at mean position. It remains same as original one. Let's go further. I will write the next part here. The second part that we want to write. That is the second thing. Second special case. That is said to be at extreme extreme position. What is the condition for extreme position? As at extreme position, what is the value of x? X equal to plus a to right side, minus a to left side. X equal to plus minus a. Put this value of x equal to plus minus a. Again this kinetic energy. Put this value in kinetic energy as well as in potential energy. Okay. As x equal to plus minus a. X square is what? A square. So a square minus a square, it is 0. What is that? That is a kinetic energy. So at extreme position, kinetic energy of particle is 0. Is that clear? Because if you put x equal to a here, a square minus a square, it is 0. So kinetic energy is 0. Now if you put x equal to plus minus a here, what is the formula? And potential energy equal to 1 by 2 Ka x square, but x equal to a, so it is 1 by 2 Ka square. 1 by 2 Ka square it is. Okay, now you can see 1 by 2 Ka square. Now what is the total energy? We want to find the equation for total energy. So total energy is what? As energy is sum of kinetic and potential, but here the kinetic energy is 0. Kinetic energy is 0. So total energy is nothing but a potential energy and is equal to 1 by 2 K into A square. This would be the total energy of particle at extreme position. This would be the total energy of particle at mean position. In both the cases, it is 1 by 2 Ka square, it is 1 by 2 Ka square, and our equation is 1 by 2 Ka square. From this you can say the total energy of particle performing simple harmonic motion always remains constant. At mean position, extreme position, it always remains constant. Okay, it never gets changed. Energy remains constant. Now this we have considered only two things at mean position and extreme position. That two things we have considered. This is mean position, this is extreme position. The energy is constant. What about the point between these two? Here, exactly in between these two, exactly at the center, in between these two, you can say kinetic energy is equal to potential. Both are equal, exactly equal exactly at the middle of these two. Exactly at the middle of these two. Okay. But when we consider any other point except the middle one, kinetic energy and potential energies varies. If kinetic energy increase, potential energy decrease in same proportion. So the total energy always remains constant. Remember, as the total energy is sum of kinetic and potential energy. So as potential energy increase, kinetic energy decrease in same proportion. That's why the total energy always remains constant for a particle performing simple harmonic motion. Apart from this, the third special case they have taken. So just remember these two conditions: mean position, extreme position. The total energy remains constant. At mean, it is due to the kinetic only. At extreme, it is due to the potential only. You must remember this point in just taken into understanding that might be the question would be asked. MCQ would be asked. At mean position, total energy is due to kinetic. Extreme, due to potential. You must remember that. Then the next point they have taken, I will write it here again. That is third special case they have written here. What is that third special case is? Just I will write here. So third special case they say that when kinetic energy equal to potential energy. When kinetic energy is equal to potential energy, we can write simple equation 1 by 2 K A square minus x square equal to 1 by 2 Kx square. This is the potential energy. This is the kinetic energy. If we solve it for x, you get value of x as x equal to plus minus a divided by root 2. Plus minus a divided by root 2. At this value, kinetic energy and potential energy are same. Just before I have told you, between these two conditions, here extreme, this is mean. Here at the center, in between these two, kinetic and potential energy are same, for which the value of x is what? Plus minus a by root 2. That they have mentioned in your book. And here, the kinetic energy and potential energy are same. And what is their value? their value is E by 2. If E is a total energy, exactly in between these 2 points, middle, at this thumb place, exactly at the middle, the energy is exactly half of the total energy. So it is E by 2. Kinetic energy equal to potential energy, it is exactly E by 2. Similarly, the fourth case they have taken. What is the fourth case they have taken? Here in this fourth case, they just find out at x equal to plus minus a by 2. X equal to plus minus a by 2. What is the potential energy? They find out the potential energy of the particle. Okay, potential energy of the particle. And if you see in your book, they have found out the potential energy of particle. Just put the value of x equal to, it is 1 by 2 kx square. Now it is potential. Put x equal to plus minus a by 2. What we get? 1 by 4, a square by 4. Take 1 by 4 common. Then 1 by 2 k a square by 2. 2 comes here. In this case, this is the total energy. So it is E by 4. The potential energy is equal to E by 4. At which point? It is A by 2. A by 2 is a point where it is exactly at the middle. If we see this diagram, 0 to n we will consider. This is n, this is 0. Exactly at this center, it is 0. Here up to n, it is x, suppose. It is x here. Then at this point, x equal to a by 2. This is a, suppose. X equal to a, actually. Minus a, suppose we remove the sign. So this point, at this point, it is a by 2. And here, what will occur? Potential energy is 1/4 of the kinetic energy. What occurred to kinetic energy? Just look at your book. They have written directly kinetic energy equal to 3 times the potential energy. Now the question comes, how this equation comes? It's very simple. Just find out the potential energy by putting x equal to plus minus a by 2. Similarly, find out the kinetic energy by putting the value of x equal to plus minus a by 2. Find out the kinetic energy. Then compare these two equations. You get this. Kinetic energy equal to 3 times the potential energy. This is homework to each and every student. Because once you just don't understand this like this, try to find out. Just we have find out the potential energy is E by 4. Similarly, by putting x equal to plus minus a by 2 in the equation of potential energy. Similarly, at your home, try to find out the kinetic energy of particle by putting x equal to plus minus a by 2. Just this equation we know. We can write this x equal to plus minus a by 2. Put it here. Find the kinetic energy and we have find out the potential energy. Equate the equation. We get this relation. Kinetic energy is 3 times the potential energy, where at this point x equal to plus minus a by 2. And for this, in your book, there is a diagram they have drawn. I will try to draw the diagram same here. Try to draw the same diagram here. And that diagram represents the variation of kinetic energy with the potential energy. So just see what they have done. They have taken y-axis. This is taken as x-axis, suppose. Okay. They have drawn the energies are like this. This is one, and the another one they have drawn like this. So this is the kinetic energy, and this curve represents the potential energy, and this is the maximum value here. Maximum value is E. At this point and at this point, both the curve meet together at the same point. So here what is occur? Kinetic energy equal to potential energy. Exactly same. Kinetic energy and potential energy are same. This is the origin O. This is the plus A. X equal to plus A. This is the point x equal to minus A. Is that clear? Somewhere between these two, exactly half. Between this and this, exactly half. X equal to plus A by 2. Here it will be minus A by 2. At this point, the kinetic energy is 3 times the potential energy. See why it's so? Kinetic energy 3 times greater at this point. This would be the potential energy. This would be the kinetic energy. See, potential energy is small. Kinetic energy is large. How much large? 3 times large at this condition. Plus as well as minus. Okay. Similarly, in your book they have written minus a by root 2 plus a by root 2. Both are same. Both are same at this point, at this and this point. Kinetic and potential energy are same. If we draw the perpendicular here, value of x is what? Plus a by root 2. Here it is minus a by root 2. Same thing they have mentioned, and this diagram represent variation of potential energy and kinetic energy. How they get vary with the total energy. Okay. But remember, total energy is always constant. That must be remembered. Let's go further. The next topic is nothing but a simple pendulum. I hope all of you have the idea. Most of the time we have considered the equation for simple pendulum. How the simple pendulum is, what exactly it is, that already we have done. We have just taken an example at the starting of this chapter. We have seen the example of simple pendulum. What is that simple pendulum? To the rigid support, some weight is attached, the spherical weight. So let's start with this simple pendulum. As its name suggests that it is simple pendulum, so it is very simple. Simple living, high thinking, that type of pendulum it is. Simple pendulum. What exactly it is? Simple pendulum we have seen up till now. It is a rigid support. To the rigid support we have attached some string. Okay. At the other end of the string, some heavy mass. This heavy mass is attached. Then this is said to be simple pendulum. But remember, here in this topic there are two definitions of simple pendulum in your book. One is said to be ideal, and other is said to be practical. See, ideal things are totally different from the practical things. Ideally, student must be regular, well disciplined. It should wear a neat and clean cloth. The student must do the homework at a time, must listen the teacher's things, and so on and so on. These are ideal things. But you know the practical things. How many of you do the homeworks? How many of you do the homeworks? How many of you are the well disciplined, well manners? Okay, don't lie to teacher or elders. This is ideal thing, but you know what you do. So that are the practical things. So practical and ideal things are different. Similarly, simple pendulum can be represented in two words. The two definitions are there: ideal simple pendulum and practical simple pendulum. Let's start with your book. I will read the definition from your book itself. An ideal simple pendulum is a heavy particle suspended by massless and inextensible flexible string from a rigid support. So see, heavy mass. This is heavy mass attached to the rigid support with this string such that it is massless and inextensible. What is meant by massless? The string doesn't have a mass. It doesn't have a mass. But practically it is not possible. Every string has little bit, milligram, microgram, some mass always the string has. But they assume ideally it is massless, inextensible. Inextensible means what? If you apply the heavy mass, it should not stretch. It should not stretch. There should not be elongation. But we know practically as we attach the heavy mass, it gets elongated. That's why the definition of practical and ideals are different. Because ideally the string should be massless, that is not possible practically. Ideally string should be inextensible, practically that is also not possible. Okay, because heavy mass is attached, so definitely it gets stretched. So that is the definition for ideal simple pendulum: is a heavy particle suspended from a rigid support with a massless and inextensible string, and other end the heavy mass is attached. That already we know. So that is the definition of simple pendulum. Practically, the second paragraph they have given the definition of practical simple pendulum. What is that? Practical simple pendulum is small, not heavy. Small but heavy, not that much heavy. Small, heavy mass, and it must be spherical, dense. Dense means what? Density is more. Dense, heavy. Practical simple pendulum is a small, heavy, dense, that is dense, sphere, that is called as a bob. As we know, this is said to be bob. Bob of simple pendulum, that we know. Heavy, inextensible spring, the small, heavy sphere called as bob, suspended by light and inextensible string. Now see, what is the definition? Here they have used a massless, here they have used a light. Light means its weight should be very small, and this word remains same, inextensible. So you can make a string or thread made up of such a material. It is very small in weight, light in weight, and in extension it should not elongate that much. So that is nothing but a practical simple pendulum definition. Now let's see what before going in detail of this simple pendulum. First of all, I would like to tell you the length of this string from rigid support to this end. From rigid support to this end, it is nothing but represented by length small l. Again, this is spherical ball, spherical heavy mass, that is bob. It must have some radius. Suppose this radius is r. Radius of this sphere is r. Then the total length of simple pendulum from rigid support to this center of the bob is a total length, and that is represented by here up to this point. It is represented by capital L equal to small l plus r. That is said to be length of simple pendulum. And when length of simple pendulum we learn, now here when the bob is moving, we move it to this side and leave it. It performs to and fro type of motion, simple harmonic motion. So there must be, as it is string, there is always tension in the string, and that tension would be represented by T dash according to the book. And this heavy mass is suppose M. This heavy mass is suppose M. So what we have said, the heavy mass M, okay, length of simple pendulum from the rigid support to center of the bob, okay, capital L equal to small l plus r. That thing we have learned. Now remember, here to understand this, let's consider some parameter according to book. I will just modify the diagram again and rewrite the diagram and just go in detail of this. So what we have learned up till now, we have learned what is simple pendulum, and what is a ideal simple pendulum, and the practical simple pendulum that we have seen. How they get differ from each other, that also we have seen. Now let's go to the theory of this. So in this theory, so this is a simple pendulum, suppose bob of spherical bob. It goes to this side, come back, again come to mean position, again it will go to this side. So this is to and fro type of motion. Little bit this might be same. I just made the different angles. So try to find out the equal things. So just this is the motion of simple pendulum. Okay. So it is a mean position as we know. This is the extreme position as we know. This is the mean position. Again this is the extreme position. Okay. Apart from this, when the simple pendulum perform this type of motion, to and fro type of motion from this point mean to this extreme like this, the string will make some angle with the initial position, this, that is said to be theta, and this length, it is said from this center to this center, this straight line length, it is said to be x. Displacement plus a minus a 0, that thing we will know. But we know the bob has a mass m, so we know this pendulum is on the surface of earth, so the total mass of the bob W equal to mg will act in downward direction. At this point it goes in downward direction like this, it is mg. But here there is some tension in the string represented by T dash, and this is L, length of simple pendulum. Tension in the string is T dash. Now what will occur, as if you remember in 11th standard we have learned one chapter, scalars and vectors. At that time we have learned resolution of vector. If you remember such type of thing we have done, it is suppose such type of thing Rx, it is Ry, the resolution becomes R equal to Rx plus Ry. We can resolve this resultant vector along x-axis and y-axis such that they are separated by 90 degrees. That is said to be resolution of vectors that we have learned. Similarly, at this point mass mg is acting in downward direction, so resolve it into two components. One should be vertical, other should be horizontal. So vertical component must be exactly opposite to this, exactly opposite to tension. So this would will give the vertical component, and here this will give the horizontal component. Suppose this is nothing but a mg, as it is component of mg cos theta, exactly parallel to tension in the string, and this which is moving toward the mean position, it is mg sine of theta. The component which is moving toward the mean position is mg sine theta. Is that clear? So this mg sine theta is a component responsible to move the spherical bob to its mean position. So what this contribute? it contributes to restoring force, as we have seen. F is equal to minus kx. Similarly, so as we go to right side, displacement increase. Okay, restoring force toward the mean position also increases. So this mg sin theta increases. Why? Because theta get increased. That is the simple thing. So we can write the restoring force in case of simple pendulum is due to this component. So we can write some simple equation. I will write dot equation here on this side. The restoring force is F equal to mg sine of theta with a minus sign. Why should be minus sign? Because force and displacement are in opposite direction. That's why there must be the minus sign, which represent displacement and force are in opposite direction. Now this is the equation we get. Okay, after resolving the component, we can find out this equation. In your book, there is equation for same equation 5.26 is there. But if the theta is very small, for example, I have taken generally sine of theta. Okay, if theta equal to 0 degrees, what is sine 0? 0. Then sine of 0 is 0. I will write here. If theta equal to 0, sine 0 is 0. Now see, if we consider this as theta, we can write sine theta equal to theta. It might be 0 or it might be very small. So use this condition. If theta is very small, less than 10 degrees, then sine theta is theta. In this equation, you can write this as equal to minus mg into theta. F equal to minus mg into theta. Capital F they have taken, so I will use again the capital F. So it is capital F equal to minus mg into theta. As we see the diagram, if this is theta and this opposite side this much is x, okay, and if this theta is very small, you can write simple formula in geometry. Might be you have learned this formula: theta equal to opposite side divided by the hypotenuse or adjacent side, x divided by L. This is simple formula. Might be all of you learn in geometry. So just that formula we have to use as theta is small, theta equal to x divided by L. Don't worry, this formula might be coming first chapter, circular motion also. This theta equal to x by L. But I hope that all of you learn this in 8 to 9 standard in geometry. Okay, so I hope you have that, you know that idea. So theta equal to x by L. Put this value of theta in this equation. You can write this as F equal to minus mg x divided by L. Now this m is constant, mass of the bob, x line due to gravity constant, length of simple pendulum constant. So these things are constant. You can write F equal to minus mg, or minus will put right, mg divided by L. Outside the bracket it is minus x. As these things are constant, so you can write simple equation: F is directly proportional to minus x. And this is the condition for what? Simple harmonic motion. So the bob of simple pendulum here obeys the condition. Force is directly proportional to displacement, but this minus sign shows they are moving in opposite direction. That means the bob of simple pendulum perform a simple harmonic motion only if theta is very small, because otherwise we can't write sin theta equal to theta. Except theta is very small, then the bob of simple pendulum perform a simple harmonic motion. So after that, we have to find out time period of simple pendulum. For this time period, again we know the equation, so I will write that equation here. Equation for time period of simple pendulum, that is nothing but what? T equal to 2 pi divided by omega. That we know. T equal to 2 pi by omega, that we have derived in last period. Last means last subsequent topic we have seen that. What is omega? They have find out this as equal to 2 pi divided by square root of acceleration per unit displacement. If you remember, we have derived it. Where we have derived it? Anybody has idea where we have derived this formula? Just go little bit back side. If we see, just little bit go back side. Somewhere you get this formula, and we have derived it on page number 115. Page number 115. That time we have derived that topic. Frequency of SHM above that time of SHM, where we have seen this acceleration per unit displacement. Okay, but as we know, force is given by this equation: F equal to minus mg x by L. From this equation we have written the force. But we know the Newton's second law of force equal to ma. So you can write this F equal to ma according to Newton's second law of motion. You can write this force as equal to ma. So this I have written F equal to ma equal to minus mg x divided by L. M from left side, M from right side cancelled out. Okay, M from left side, M from right side cancelled out. After that, what we get? A equal to x by L. G x divided by L with minus sign. Take this x to this side, you get acceleration per unit displacement. A by x is equal to minus g by L, and A by x is nothing but this acceleration per unit displacement. So put this value of A by x here. You can write this time as, I will write here above now. You can write this time as equal to 2 pi divided by square root of this thing minus g divided by L, or you can write this as 2 pi square root of L by g with a minus sign. Suppose I have neglected the minus sign, then this is the equation for time period of simple pendulum. So T equal to 2 pi square root of L by g. 2 pi square root of L by g. That is the equation for time period of simple pendulum. So that is equation 5.28 from your book. And remember, here there are some conditions they have mentioned. The bob of simple pendulum performs simple harmonic motion. There are some conditions they have given. What are that conditions they have given? 1, 2, 3 in your book. The first one, amplitude of oscillation is very small. This is the amplitude. This must be very small, at least 20 times smaller than the length. In our case it is large because it is magnified view. But practically this should be 20 times at least less than the length of simple pendulum. Then and only then the bob will perform simple harmonic motion. Second, length of string is large. That is same thing. It should be large. This should be small. Third one, during the oscillation of bob, it must move in vertical plane. So it is vertical plane. It must goes to and fro. In this plane it will move vertical plane. This is my hand as a vertical plane. It will move in vertical plane. And its frequency they have given. As we know, frequency is reciprocal of time. If this is a time, the frequency is what? F equal to 1 by t. What is that? 1 divided by 2 pi square root of g by L. That is nothing but a frequency. The same thing they have mentioned in equation 5.29. Now from these equations you can write some formulas, or just we can write some conclusion from this equation. Basically, time period of simple pendulum, T equal to this. From this we can do some conclusion. The first conclusion says that time period of simple pendulum T is directly proportional to square root of length of simple pendulum. As it is related to length, it is said to be law of length. In your book just they have given A, but that is said to be law of length of simple pendulum because time period is directly proportional to square root of L. G and 2 pi are assumed constant. Okay. Second, they have taken the time period is found to be inversely proportional to square root of acceleration due to gravity. That's why it is said to be law of acceleration due to gravity, because it represents acceleration due to gravity. While doing this, assume length is constant. 2 pi is always constant. And third one, from this equation again, time period does not depend on mass. Time period T does not depend on mass. Here there is no M term. M is not there, means there is no mass because we have cancelled it here. So there is no mass in this equation. So time period is independent of mass, and that is said to be law of mass of simple pendulum. Law of mass. The next one, the time period does not depend on amplitude. Here there is no X term or there is no capital A. That means what? Time period does not depend on the amplitude of SHM, and that is said to be law of isochronous. Law of isochronous of simple pendulum, which shows that time period is independent of amplitude. And after that, there is a next topic, seconds pendulum. What exactly seconds pendulum is? As it is simple pendulum, it is very simple pendulum. Now I have just made simple pendulum as seconds pendulum. Time can be measured in seconds. So seconds pendulum. So seconds pendulum means what? The simple pendulum whose time period is always 2 seconds. That is said to be seconds pendulum. It start here, so start here, goes here, again come back here within 2 seconds. That is said to be seconds pendulum. And for that, as we know, the equation for simple pendulum, we know T equal to, as from this equation, 2 pi square root of L divided by G. This equation. And this must be equal to what? 2 seconds. This 2 cancel with this 2. Square both sides. What do we get? This implies that pi square L by G equal to 1. Pi square L by G equal to 1. What is L equal to? This implies that this L equal to G divided by pi square. And this is length of seconds pendulum. So they have taken here as L suffix S. Seconds pendulum. Otherwise, this length and this length become same. That's why LS stand for length of second pendulum, G divided by pi square. From this formula, once you know the acceleration due to gravity at any place on the Earth's surface or in universe, at any place you know the G, you can find the length of second pendulum. Or if you know the length of second pendulum, you can find out the acceleration due to gravity of any planet. That is very simple. Just create a simple pendulum, find out the length of seconds pendulum whose time period is 2 seconds, and then just by using this formula find out the, then by using this formula you can find out the acceleration due to gravity. Okay, just create a simple pendulum whose length is, whose time period is 2 seconds and length is suppose Ls. Just put this Ls into pi square, it will give the acceleration due to gravity of any planet. So in this fashion we come up to this. Apart from there are some equations, so some problem they have solved. Try to understand that problem first, how they will use the formulas and what they have asked in the numerical. Just concentrate on that first. Accordingly, you try to understand that numericals. After that, on the next page there is activity. In this activity, nothing is to explain. Just look at the table. In that table, what they have taken? Theta divided by T theta divided by T0. The ratio of time periods they have taken. Ratio of time periods with theta. Theta is some angle other than the 0. T0 is nothing but a time period at 0. Theta equal to 0. Time period at theta equal to some value, non-zero value, at T theta. Their ratio, if you find out, for angle 20 degree, it comes to be 1.02 in your book. And 45, 1.04. 50, 1.05 and so on. In this case, if you find out error in percent, for 20 degrees Celsius, the error is 0.02%. No, not 0.02, it is 2% for 20 degree. 45 degree, it is 40%. Okay, 2% for 20 degree. And 45 degree, it is 4%. 50 degree, it is 5%. 70 degree, it is 10%. And 90 degree, it is 18%. As error get increase if you increase the angle. So as we assume the one condition while doing simple pendulum, this theta should be very small. How much small? At least it is less than 20 degree. So 20 degree means what? The error of 2%. And for that they have mentioned that table. That's it. So theta must be very small. Otherwise this bob will not perform a simple harmonic motion. Why? Because error increases if theta get increased. So theta must be less than 20 degree. And it is best if theta is less than 10 degrees. That is nothing but a simple pendulum, seconds pendulum. After that there are two columns they have taken. Difference between conical pendulum and simple pendulum. Just try to read this difference. As already they have mentioned, the formulas they have given 0.4, the formulas are different, and some 5 point they have mentioned. Try to understand this and read it. Nothing to explain is there because we have not learned the conical pendulum up till now. When we learn the conical pendulum, at that time I will tell you the difference. I think there is no need to tell you the difference at that time also, because automatically you get idea about simple and conical pendulum. Today, quite difficult to tell you the difference between the two conical and simple pendulum. You can understand well when you consider the conical pendulum also. When you learn the conical pendulum, we have learned the simple now. When we learn the conical pendulum, you can find out distinguish. So just read it and prepare it for sake of your understanding, and it is better for point of your examination. This type of point may be asked. You to distinguish between the conical pendulum and simple pendulum. So you should prepare this. The next topic about syllabus is what? Angular SHM and its differential equation. Up till now what we have seen, simple harmonic motion in straight line, that is said to be linear simple harmonic motion. Now next period we will start with the angular simple harmonic motion. Its equation we have to see. Then we have to see some damp oscillation, pre-oscillations and force oscillation, and finally we'll consider resonance and we'll finish the chapter. I hope only one video is remaining now to finish the chapter. So before reading the book, first of all see the video, understand the point, then read the same topic whatever I have taught you here in your book, then you get a better understanding. Okay, still if you have any problem you can call me. Thank you.